Hi everyone, good morning. Welcome back. All right, let's go ahead and get started. Welcome back everyone. So we have a very interesting session prepared for you today. If you remember, on Monday we had Dr. Stephen Jordan from Google talking about the DQI technique, which was a very new and exciting technique in optimization. And today we are going to do a hands-on session on it with our wonderful Catalina. Catalina, as you know, she's been with us before, and she's amazing, and she's like very hands-on and talks, you know, Helps is going to do a deep dive into it. Catalina is a quantum community manager at Xanadu, where she works closely with researchers around the world to help them leverage PennyLane and ensure that it remains a premier software tool for quantum computing. And she's been a driving force in quantum education. She's led PennyLane's educational initiatives, organizing events like QHack and Quantum Software Workshop, and she gives talks and workshops globally. And she has been a wonderful part of the Wiser community. I have to say, she's been with us for multiple years, giving talks and hands-on sessions on various different topics, and we're always very happy to have her with us. So okay, let's get started. Please join me in welcoming Catalina. Over to you, Catalina.
Thank you so much. This was a really kind introduction. It really was my heart to see everybody here and everybody coming. And thank you to Wiser for organizing these programs. They really make a difference. So with that in mind, I'm gonna get started. So today you're in for a treat. Let me just get this in slideshow and get this going. So we're gonna talk about Dakota quantum interferometry. I'm gonna be on the Discord, and so please feel free to ask your questions there. Now, who attended the session on DQI? Who attended the previous session on DQI? Give me a message in the Discord. This is a very interactive session. For those of you who have not participated before, you cannot really do other things. You have to actually be here in the session today. So I see a lot of engagement. All right. Now, who participated in the session that I gave in the Wiser Quantum Algorithm Fundamentals program? So who is here for my previous session on in the spring? I think it was in May or April. So who is here for my previous sessions? Anybody? I guess less people, maybe a couple. All right. So you probably already have a sense of what DQI is. If you have ideas of like things that stuck with you about DQI, send them in the live questions chat. I want to see kind of where we're starting from. But the main goal today is going to be for you to get the tools to actually learn this for yourselves. I am not a DQI expert, and this is going to be weird to say. Like, why are you giving us a talk if you're not the expert? There are a lot of people that know more than I do. However, I'm going to share these tools so that you can learn and that you can become then experts, and you can actually know more than me, hopefully. So that's the plan for today. I'm going to be asking questions in the middle. You can also ask questions. I'm going to be looking at the chat, and hopefully we can make this interactive and we can all learn together. So let's get started. A little bit about myself. I actually am now research engagement manager, senior research engagement manager. This is work that I have been doing for a few years now, for a while. And the main purpose is to bring the research closer to the software. So bring the latest research into the software and bring these tools that we have in the software to the researchers so that they can do better research. So that's the main thing. So DQI is one of those examples where we recognized there was this new way of doing quantum optimization, and we brought it quickly into educational material that you could use. So that is what I'm going to talk about today. It's part of this mission of getting all of this useful quantum computing. Like this is still research. We'll still need to figure out what this is going to be used for. It's great to have a lot of people here in the chat today because I want you as well to think about how to use this. And now, if we think in a different way, so the plan for today is to think in a different way about how we do quantum computing and use these tools for that. So with that brief intro, if you had a 200 qubit quantum computer, what would you do with it right now? If you want to answer in the chat, go ahead. Usually getting to the details of how do we do useful quantum computing is very hard. So there are a few areas. So somebody's saying study the quantum system. Yes, There are many different applications, and you're going to hear people saying, I'm going to do optimization. But when you get into the details, it's actually pretty hard. Developing a new algorithm, developing one that scales to useful problems is really hard. So the problems that I have here are problems where Xanadu has developed algorithms. None of these actually are using DQI, to be fair. But I want you to think about other problems where maybe a new way of thinking about optimization could help. So what is optimization? Feel free to answer in the chat for the questions that I ask. Is this process of finding the best solution out of a set of options, right? So we have all of these options to optimize whatever problem. We're going to find the best solution. In quantum, we're going to use the properties of quantum mechanics, so superposition, entanglement, and interference. So we're not just going to try brute force or smart classical algorithms. There are a lot of smart classical algorithms for optimization. We're going to use certain properties in order to achieve this optimization. There are many ways to do quantum optimization. Some are QAOA, adiabatic quantum computing. There are many different options, many of them including like Hamiltonians and evolving a Hamiltonian until you reach a ground state. However, today we're going to look at a different way. So we're going to mostly focus on interference. We're going to see how we can encode problems in this space where you can interfere the solutions until you get the one that actually optimizes the problem. So this is a new tool for your toolkit, and hopefully you'll be able to make the most with it. Quantum interference works like waves. So this might be easy for you. For some of you, it might be hard. But the point is, you want to engineer how these patterns perform, right? You don't just want to throw some light into the slits. You actually want to make sure that the right answer amplifies and the wrong ones cancel out. So that's where quantum interference is used. And we're going to use a quantum computer here in the middle to modify these probabilities. So at the end, we're going to measure one sample. So in reality, when you use an actual quantum computer, you don't get access to the whole state. You can just like take a number of samples. You can run the circuit, get one answer, maybe run it again and get another answer. And so you want the right result to have a high probability. So you want that when you sample, you have a high likelihood of sampling from the correct result. We can engineer the way that we encode problems by adding them into the amplitudes of the state, for example. So the probabilities here, the probabilities of getting a 0, 0, 0, 1, 1, 0, and 1, 1, so on, they depend on the amplitudes of my state vector. So here on the right, I have a state vector with some x's. They are these coefficients that tell me kind of, this is my state, and I can represent it as complex amplitudes, some coefficients of my state. I want to engineer those. So I want to encode some data into those amplitudes. I will add some gates. There will be some state preparation routines. So maybe for a different session, maybe for the next Wiser program, we can talk about state preparation, which is a whole big thing. But today we're going to look at just one, which is amplitude encoding. I'm going to encode my data into the amplitudes of my state, which are these coefficients that you will have seen, coefficients of these, basically the coefficients of my state. This is very hard to do. So to be fair, it's not obvious how to do it, right? How do I encode this sine function into the amplitudes of my state? It's not obvious. So I know the picture is really tiny, but here you have the states from 0 to 30, and you might want to encode, the probability of getting 0 is really high, and the probability of getting 3 is kind of low. So you're encoding a sine function in the amplitudes for each of these states. This is very hard to do. There are a lot of very inefficient processes to do that. So maybe we can work in the frequency domain. If I want to encode a sine function, maybe I don't need to encode all of these numbers, right? You can represent a sine function with kind of like just maybe one frequency. So we can use the Hadamard transform to do that. We add Hadamards at the beginning. This is the Walsh-Hadamard transform. So we can add Hadamards at the beginning of my circuit. Then I add a routine that encodes some problem. And then at the end, I transform back. So I move to Fourier space, and then I move back. Depending on what kind of information you want to encode, this might look a little bit different, but basically you add Hadamard's and that moves you into Fourier space. That's kind of the easy way to see it. In the picture here, what you see is the example of different frequencies. So if you see these waves, the blue one has a lower frequency and the green one has a higher frequency. So you can use the gates to encode these different frequencies or to modify how they behave. Here you see another example of how this Hadamard transform works. We're moving from just state 0 to state 1 to actually rotations around the equator of the Bloch sphere, right? These look a little bit like a clock, so they're periodic signals, some with a higher and some with a lower period. So when you hear phase, when you hear that phase is very important, that's because we're moving here in the equator of this Bloch sphere. The information here is mainly contained in that phase for your the phase for all of your coefficients. All right, so that's kind of the big summary. The DQI algorithm, which we're gonna talk about, it has a few different steps. The first one is we're going to encode the weight coefficients. Then we're gonna prepare some states. They're called DQI or DIC states. I don't know how to pronounce that, but basically we're gonna prepare a certain set of states which have some characteristics, and then we're gonna do some computation and non-computation. So we're gonna basically use some tricks. We're gonna use some tricks to modify these frequencies. So that's what they call the computation and uncomputation. And a lot of this, when you see it, I don't know, this is how the previous speaker explained it, but a lot of this is explained in the terminology of quantum error correction. You're going to hear about syndromes, for example, right? You're going to hear about decoding, right? These are all terms that come from quantum error correction. So if you are interested in learning the terminology, then that's a place to go. Learn a little bit of quantum error correction, and it will teach you what these, like, why these are called syndrome and why these are called decoding and so on. The main thing for me is not that you understand the exact, why, like that you can we can leave it for another session, but how you can actually do it hands-on. All right, so finally, just I told you that encoding the information is hard, right? Encoding the information, the amplitudes is not so easy. One way of solving that problem is you do this Hadamard transform, and then you get sparse data. Instead of encoding all of this sine function, you basically are encoding the frequency that it is working on. And so you're kind of having to think about the problem differently because you're no longer just looking at the data, you're looking at other kind of components of the data. And so by encoding this data directly in the frequencies, it might make it just easier to prepare and more likely to be useful to scale to useful problems. The example that we're going to look at today is called max XOR SAT, max XOR SAT. And the main thing is we have a linear problem, right? We need to find the excess that maximize the number of constraints being satisfied. So for example, in the first one, I have x0 times 1 and 0 times x1, 0 times x2, and 0 times x3. So I only have x0, and my constraint says that it has to be equal to 1. So x0 equals 1. That's the first constraint. And for the second row, we do the same, right? So x0 plus x1 equals 0, and so on. So I have a number of constraints. I want to satisfy most of them as much as I can. It's not always obvious that you can satisfy all of them. You may not be able to satisfy all of them. So you want to satisfy as many as possible. That is the question. How can we find these excess? This problem scales very quickly. It's a combinatorial optimization problem, and it's not. If you have 100 x's, it's just too hard to do. So we're gonna try this new recipe where we do a little bit of this this magic, right? Where you encode the information in Fourier space, encode the constraints by adding this phase. Remember how we saw these little circles? We're gonna encode the constraints as a phase. Then we're gonna encode the matrix by adding a certain set of gates. And finally, I'm going to do the decoding, basically finding the right answer. In this case, we're going to use a lookup table. This is like cheating. You cannot really do this with a lookup table for real, very big problems, but you can do it like these. You can use lookup tables for a small example. In reality, you would need other techniques, other decoding techniques. So this is where the quantum error correction stuff comes in. It's hard to do, but it's possible. So you probably heard a little bit of this in your previous session. Let me know how we're doing so far. Are we good? Let me know. Give me a reaction. Give me some questions. Okay, I see some good reactions. Perfect. Excellent. Okay. All right. This is kind of the TLDR. So let's see this in action. And for that, you can use this. I'm going to share this website. All you need is a PennyLane account, but it's free. So I'm gonna share it in the live chat in the Discord. It contains a few notebooks, but it includes one that says DQI. So I'll give you a second to get to the notebook. Just look for the DQI note. So you should get to a page that looks like this. And at the bottom it says download materials, and you're gonna be able to find the DQI tutorial. So I know that I usually do this with live coding. Today it's a lot of code, so that's why we cannot do the live coding today. But I'm gonna show you the code. Okay, so give me a reaction if we're ready, or send me a message in the Discord if you need a second. Okay, we're ready. Perfect. Let's get started then. As always, we, if you're using Colab like myself, you would just pip install PennyLane. Make sure that you're using the latest version of PennyLane. You can check this with, if you import PennyLane as QP. This is the new way that we import PennyLane to say this is quantum programming. It's not only for quantum machine learning, it's for quantum programming in general. And we can write qp.about. You can use Google Colab or Qrate or your local computer. Just make sure that you're on the latest version of PennyLane, which is version 45 at the moment. All right, so with that in mind, let's remember the problem that we're solving. We're solving this max XOR SAT problem. It's a linear system where we want to maximize the number of constraints that are satisfied. By now, I know that all of this program is about optimization, so I hope that you understand why an optimization problem can be mapped to this kind of just linear vector and matrix problem, basically. All right, so we have this problem. We want to maximize a certain objective function. So again, you've been doing optimization for a little bit. You know that in optimization, we need a function that we're going to maximize. And this function is going to contain all of the information that I need in the problem. Maybe I'm going to make this a little bit bigger. This function that I'm going to maximize, it contains the information for my constraints, right? My v vector at the end of my problem. Let me actually bring back the problem here just for a second. I have my matrix B, the information from the system, my vector v. For this particular problem, which is XOR SAT, all of these numbers are binary. It's just ones and zeros, and we're going to stay always in the binary ones and zeros. So everything we're going to do is modulo 2. So I have the information of my v's, of my b's, and I have my x's, which are the ones that I don't know. The x's are the ones that I want to find. So I have this function that I want to maximize, because this is going to give me this is going to maximize the number of constraints that I have. I'm going to use NumPy. I'm going to import it from PennyLane. Just you can import it as PNP or as NP, however you prefer. We can write the matrix B and the vector V as NumPy arrays, so PNP arrays. It's PennyLane NumPy arrays. So here we have the two vectors. I actually didn't check if they're exactly the same, but I think they should be the same. And now I can get some information that I need for my problem. So for example, I'm going to take a number of samples. I want to know the shape of my matrix. I can extract this information quickly. So the shape of my matrix is going to be M and N, and I'm going to use the transform, like the transpose of my matrix B. I'm going to call it BET. So these are just some kind of constants. These are some useful information from the problem that I'm going to use. I can create my objective function as just a normal Python function. So I hope everybody uses Python. So I'm going to just use this objective function, this Python function, to create this objective function, which is going to depend on X. So if we look here, this objective function, which I'm going to maximize, basically what we're going to do is we're going to find the right X that minimizes this function. So all we're doing here is we're putting into code what we had in the math, the function that minimizes, that gives me the right solution, minimizes the cost. We're going to have to sample. So we're going to take some samples from the problem. Remember how I said we're going to have some probabilities, but at the end, we're going to take some samples, and we're going to use this to give us kind of some information. about the right answer, right? If we're getting the right answer or not. So let me make this a little bit smaller so that it can just fits. No, it doesn't fit very well on the screen right now, but you can basically see that there is one answer that is very, very high. Basically, this is the right answer, and I have a very high probability of getting that answer. So that's all it's doing. I have the right answer, and it's giving me, there's a very high likelihood of getting that answer. Now for the algorithm, I'm gonna skip a little bit of the details, a little bit of the math. You can look at this later. You have the tutorial. It's also on the PennyLane website if you want to see it there. The main part is how do we do it in the code, right? And we're gonna get back here if we need it. So the thing that I like the most about this tutorial is you have this really nice diagram that tells you how how the information is moving and what the process is like. So you start with your weights. You're going to prepare these states that contain the weights that you need. These weights are, there's something called the DQI states. Basically, they, based on a certain value k, they're going to create some states that have the same probability of getting sampled, right? So you're going to get some states that have the same probability depending on how many ones you have, right? Depending on how many, I know this is a little bit confusing, but let me go back here. Depending on how many ones you have in your matrix, you're going to prepare some states that have the same likelihood of being measured at the end, right? So the states that have 2 ones have the same likelihood, and the states that have 1, they have a different likelihood. So those are the states that we're going to prepare, where they have these weights depending on kind of how many ones are in that state. All right, so once we prepare those states, we can do some modifications. We can add some error register. We're gonna basically modify these states. We're gonna modify these states to alter the probability. So remember how we said we first have to encode something, and then we have to modify the probabilities to enhance the chance of getting the right answer. So that's what we're gonna do here. So far here, we don't have information on the problem. We just have some states that we're preparing, and that's all. We don't have information on the big V and the big B. This is just the preparation of the problem. Now the encoding part, this is where we actually start adding information. This is where we add the phases. So if you look here, I have this -1 to the little v, because this is going to create, if I have a -1 and the v is a 0, that's actually turned into a 1 and a positive 1. And -1 to the 1, it stays as -1. So this is what is going to add these phases. Having this -1 to the power of v times y, this is going to add the phase. So this is just a smart way of adding these phases. In another way of thinking about it, if you have the state 0 and you add a Hadamard, you get into the positive x-axis. You get the plus state. You're in the negative z-axis if you're in the state 1, and you add a Hadamard, you go into the minus state. And these are states that are basically both on the equator, but they're separated by a phase of 180 degrees. So having these -1s to a certain number kind of has this power of allowing us to move the phase along the equator. So along the equator of this block sphere. Now, after I have encoded this vector v as like in the phases of my problem, then I can add my matrix B, right? So I'm going to add a new register, and this register is going to add some extra information that I can use to add basically that information. I'm going to combine the information that I had before, which had kind of the V vector encoded in the phases. I'm going to combine it with now my problem, my matrix B. And once I have that, I just need to kind of let the problem solve. I can just resolve the answer of the problem, right? I can decode, and I can do the final Hadamard transform to go back into, let's say, direct space instead of Fourier space. So this was a lot of talking, but hopefully you can see it here in the code. The first section here, we are calculating these weights. So these weights just are, this is some math to calculate them, but you're going to see that you don't have information here about the problem. You have some registers. These are the registers that you're going to use here, just different parts of the problem. If you look at the quantum circuit, and let me see if I have a a diagram somewhere. Maybe let me go here. If you look at a quantum circuit, you can say the first two qubits are the first register and the second 2 qubits are the second register, and I can have more. This is useful just as a way of mentally separating them and to adding operations in them in a separate way. They're actually still part of the same program. It's just different components of the program. So I have these registers that I'm creating here just for ease, and I'm calculating these weights. These are just diagonal matrices that are going to help me calculate the weights, and I'm going to find some right values for these weights to prepare those states. Yeah, that's it. So far, just some static parameters that are kind of dependent of the problem a little bit. I have this this weighted superposition depending on the state. I will prepare a different coefficient for each of these states. In PennyLane, we can use state prep. This is just an easy way of preparing states where I know I want them to have a certain coefficient. I can use QP.state prep to prepare those states. The hardest part here, I think, is just understanding the math on how we prepare these states. But at the end, once we know what are the weights for the states that I want to prepare, then I can just use state prep and it will do it for me. Now these DQI states, again, the math is a little bit tricky, but you can look at it a little bit later. I can create these state vectors. So just to clear, all of this is a state vector simulation. This is not designed to run on a large scale so far. This is a toy example. Hopefully it can help. I can create these state vectors of the amplitudes that I want to prepare. So now, because I'm going to be working in the Hadamard basis, I need to know what the amplitudes are going to be. So all I'm doing here is for each of the amplitudes, I'm gonna have this dictionary, the state dictionary. I can now implement, I can add some CNOT gates, some 2-qubit gates and the 3-qubit gates. They will help me implement the unitary that is going to add the information to the problem. So here you have it, depending on the specific unitary that I want to prepare, then I have a set of mini unitaries that I can create there. So all I'm doing here is I'm kind of preparing the work in order to be able to encode these amplitudes, so prepare these DQI states. I just need to do a little bit of processing, that's all. So once I have these kind of functionality that helps me implement them, I can just call them in my function that prepares the DQI states one by one. I prepare the SCS, I prepare these split and shift cycles, I prepare these unitaries one by one, so I can call them as needed in my function that prepares the DQI states. All right, so finally, so far, we don't have any Q nodes. If you look here, these are functions, but they don't have this at qp.q node. So maybe before we go there, is there anybody who is new to PennyLane? Is there anybody who doesn't know what a Q node is? Well, I see we have a few questions. B is not a square matrix. Not necessarily. B doesn't need to have a square matrix. No, it doesn't need to be a square matrix. What is the difference between PennyLane NumPy and just NumPy? The PennyLane NumPy is useful when you want to do some optimization. It has some functionality that's designed to work with it. You don't always have to use it. If you're not doing optimization, then you don't need the PennyLane NumPy. All right, let me see what else do we have. We cannot differentiate in the standard run. There we go. Okay, how to understand the output after the compile. We haven't gotten there yet. So when mapping an objective function into an interferometer, how do we prevent the optimization from getting trapped? The algorithm needs to do that. So some algorithms, for example, QoA doesn't guarantee anything, right? Some adiabatic problems, they don't guarantee anything. The algorithm itself, so you just choose an algorithm that guarantees that. But if you have an algorithm that guarantees that, it might be more expensive. All right, so far we have prepared the DQI states, and now we have the Q node. So I'm assuming everybody here knows PennyLane. You know that we create a device. This time we're using default qubit. Hopefully this should be familiar for many of you. And now we create this Q node that attaches the specific quantum function to the device. So this specific Q node takes 3 arguments: the size of the matrix B, M and N, and L, which is just like some length that I defined earlier. Now we can do a controlled preparation of these DQI states. So depending on the value of K, I will prepare a certain state that will have a certain amplitudes. So that is what I'm doing here, depending on the value of K, which are the number of ones in my state that I need. And so at the end, we have some states. Let's say the state 0, it has a certain, a certain coefficient, and the state 0, 1, like 0, 1, 0, 0, and so on, it has a different number. And so each of them have a different number associated to it. And if you look carefully, all of those that have two number ones have the same number, or basically the same number, right? And all of those that have 3 ones have the same number. And the one that has 0 has a different number. So these are the decay states. Like, depending on the number of zeros or ones that you have here in your base state, then you have a different coefficient with a different number. So all of those that have two ones have basically the same coefficient. So that is kind of the main thing there. Now we can do the weight register. So for the weight register, this is, we're going to generate some bit strings, and we're going to uncompute. Basically, we're going to kind of like if you've ever done a Rubik's Cube, you have to kind of move things back and forth. This is kind of the same idea. You're moving things back and forth so that you actually get kind of, you get the movement of the probabilities in the way that you want. So you place some specific number ones in the right positions so that you're amplifying the right probabilities and reducing the other ones. So this is kind of just a technicality. I wouldn't worry too much about that. You can read more about it later, but it's just this way of kind of moving the probabilities in a way to discard like the things that we don't need and keep the ones that we do. Now we're going with encoding. So I mentioned we use this -1 to the power of Vy, which helps us encode the information as a phase. So I can use state prep again. I can use another keynode with the same device, and I can encode the information in the constraints. Here I use state preparation again, and I can encode the information from V. So I have this phase function that is going to encode the V information, and I'm going to add it as part of my encoding part of the program, basically, right? So at the end here, I'm going to print some states, and you're going to see that the probabilities have been modified. Some probabilities are now negative and some are positive, and this is how I'm going to interfere them. So the details, again, don't worry too much about them. You're not going to remember them anyways, that's okay. But just know that at this point, I changed from having the same number for each, let's say, number of ones to ones that are positive and ones that are negative, because they have encoded a phase in them. And finally, now I can encode the actual, core of the problem. I can encode my matrix, and my matrix is just going to be encoded as a set of C naughts that depend on the values in my B transpose, right? So depending on this value that I had in my matrix, I will add a certain C naught. I would add a C naught or not. So these C naughts kind of do this conditional, operations that help me, again, modify these probabilities. The syndrome just helps me basically do that. So here, again, I don't have the Q note. This is just the helper functionality, this BT multiplication. I'm going to add it here as part of this thing that they call syndrome preparation. Again, don't worry too much about the terminology. You can learn where that comes from later, but just know that this is kind of related to this error correction stuff. So I can prepare my states. I have the same state vector that I had before, right? My raw state vector. I can do the multiplication by adding these C naughts of my B. And finally, here I can see I have like a different modification. I haven't compared it exactly with the vector that I had before, but now I have basically, instead of having like a slower number of zeros and ones, I now have a full extra, a whole extra section at the beginning. So here I had 1, 2, 3, 4, 5, 6. I cannot count, but like 7 zeros, something like 7 zeros. And here I have more, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I have 4 extra. This is the length of my matrix B. I have 4 extra zeros, which help me encode. And if you see here at the bottom I have the ones, where in those 4 extra zeros, I have some ones. I have some ones here at the bottom, and they're going to modify again the way that it works later. So at the end, this is where we do the decoding. This is where you kind of finalize your Rubik's Cube. What we're going to do here is we're going to kind of add a lookup table. Again, this is because the problem is small enough, I can kind of tell it based on information that I have in the lookup table. Then I can decode. I can kind of find the right answer based on the right information from this decoding. And at the end, I have a final Q node. I have some shots. I can prepare the state that I had before. I can just use or apply this decoding table. So I'm going to apply some controlled some control operations depending on what I had here in my decoder. So at the end, I have my very big, much larger program now because it has like these extra set of qubits that I've been adding, and I have a different answer. This gives me basically these numbers here tell me how many samples I got. I had a number of samples that I had set at the beginning, and I sampled and I got a very high likelihood of measuring, for example, the state 0 or the state here with 1, 1 over here. Now, this is not enough. Remember at the end, we said we have to move back to direct space because we don't know what this actually means. We're working in Fourier space. And so all we're doing here is we're moving back. We have to transform again. So I'm going to apply the whole thing together. This is just everything that we did together. We're going to embed the weights that are going to help us prepare those sticky states that have the same probability depending on the number of ones. Then I'm going to on compute, so this is kind of getting rid of the things that I don't need and keeping the ones that I do. I'm going to add the phases that encode the vector here that I had at the end. Now I'm going to add the information from my matrix B. And finally, I'm going to decode according to my lookup table so that I get, the probabilities to interfere in the way that I need it. And finally, I'm going to transform back. I'm going to apply the Hadamard transform. I'm going to count how many samples I got. So if I run this, so all I'm doing here is I'm running the function that I created right before, and I'm gonna show you the probabilities. I get a very high probability of measuring, 0011 and 1101. It's not perfect, depends on the number of samples and the problem and everything, but basically it kind of tells you like if you do DQI, then you actually get the answer that you really needed. So I know this was a lot and I don't have the time to stay for questions, unfortunately, but I will show you, where you go next. So first you have the information there and you can go to PennyLane.ai. If you want to use PennyLane for education, we have a lot of resources for that. And you can go to the codebook and to the demo. So you're going to see it there. If you have more questions, then please go to the discussion forum, discuss the PennyLane.ai, or you can ask them here in the chat. I will come back later. I do have to go now, but I will come back in a moment. I will come back later today and answer your questions. Again, thank you for staying. I know this was probably the hardest session that I've taught so far. This is hard. This is really state of the art. This is new. It's still being built. So I just wanted to give you a little bit of a flavor of kind of how to interpret all of this. You can later look at the math, but hopefully this gave you a little bit of insight on why all of these steps are happening. So thank you again. And I'm sorry that I have to leave, but yeah, I hope you enjoyed the session. Give me some reactions. How are you feeling? I hope not too confused or maybe a little bit motivated to learn more about this. Yes? Okay, great. That's the main thing. It's hard to learn the first time, but hopefully this motivates you to keep learning about this. All right, awesome. All right. I think we're doing good. I'll be back later to answer the questions. So you have a little bit of time to look into this a little bit more and ask the questions. And thank you, Vardan, again for the invitation and everybody at Wiser. Remember that we have a challenge. I forgot to mention it today, but if you looked at the website that I shared, there's a challenge that you can solve. You solve it in time. If you solve it for the 15th of July, I believe is the date, then you can get a PennyLane Wiser certificate. So yeah, I hope you can solve the challenge. I want to see all of those certificates on LinkedIn.
Beautiful. Yeah, and thanks a lot, Catalina. I do know that you need to rush, so I'll let you go. But thanks again for the wonderful session. And to all the participants, just like Catalina mentioned, keep the questions coming on Discord. She is on Discord. She's pretty active over there as well. So yeah, we can get to your question.
Awesome. Thank you very much, everyone. Bye.
Thank you. Bye. So yeah, with that, we'll wrap up this session. Thank you, everyone, and hope you have a great day ahead.